So, the title, as you can see, is Derivatives of Inverses, and first a bit of review of the pre-calculus ideas. Can you make a table of the inverse in 5 seconds? Go.
The order's a little weird, but it's like it's sending X to the other one, and then sending
That's fine. I would do the same. Okay. So, give me some points on the inverse. 7, 0, 11, 2, 4, 3, and 2, 5. Okay, easy enough. Numerical is the easiest first. Just switch the X and Y. Boom. Okay, now let's talk analytically. Find the inverse of f of x equals x plus 2. Let's not overthink this. What's the opposite of adding 2? Subtracting 2. So we can say that the inverse is x minus 2. Okay. Now, a note about notation before I go on to the proof thing. I prefer inverse function notation over y. So I'm going to call this mini lesson, y is f inverse better than y. Well, if I have y equals x plus 2, and I switch, then x equals y plus 2 is the inverse. Do you agree? And yet, is there anything in there that shows that one's the original, one's the inverse? Or does that y look exactly the same in both cases? The limitations. There's no real distinction between the two, and yet one is the inverse. When you do function notation, and I say f is x plus 2, then x is f inverse plus 2, there's no doubt those are different. One shows the function, one shows that it's the inverse. All right, so because inverse function notation allows you to show there's a distinction, that's why I prefer it, assuming that the inverse is a function, which is actually an assumption. So let's go back here. Say, Elizabeth, are you feeling mentally fresh and smart? Okay, that's okay, because this question is super easy. If I take 5 and add 2 and subtract 2, I get 5. Let's get a quiet question. Mr. Butters, you real quiet. What is 9 plus 2 minus 2? Well done. Yes, wow. I am happy you spoke down. Larissa, what is any number plus 2 minus 2? Any number, okay. So we could say that when you run any number through a function and its inverse, you're right back to the number. Mathematically then speaking, we could say when you put the inverse, actually let's say this, when you put something into the inverse and then that into the function, you're right back to where you started. Do you agree? And that's also the case if you put a number into the function first and then put that into the inverse, you're right back to where you started. You prove inverses then by saying f of f inverse can be shown to be just x. You did that in Algebra 1 a lot, and we won't do that here so much. But that is actually the final point, or the starting point for derivatives. So we'll go back to that in a second. Would you find the inverse of that function implicitly, please? That should take 2 seconds just to write. 1, 2. So, implicit. What is your derivative? Your inverse implicit? X equals to the f inverse plus 3. Implicit means implied within, not clearly stated. Implied within, you do not have to solve. Okay? Implicit means not solved for. Implied. If, however, I talk explicit, that doesn't mean, dirty words on a record. That means clearly stated, explicit. Then that means solve f inverse, or find f inverse. So, would you please find f inverse explicit? F inverse is x minus 3 over 2, and what of that? Natural log. Okay? Do you all concur? Okay, let's move on. All right, let's talk graphically then. If you are telling your younger sibling to how to graph that there at the end of the green book, you would say, well, that's the shape of a... No, I think you're missing that piece there, buddy boy. A cube with what attributes?
0 at 0 and negative
0's at 0 at negative 2.
2. Double root.
A double root at negative 2, and what happens graphically at negative 2? Why does it do that? Because it's a double root. That's just kind of answering the question with the same thing. Why does it bounce, not pass through? Because it's squared, and you will not change sign around a square. Do you agree? Okay, so that's the original function. Would you graph in a dotted line kind of fashion, or a different color if you have colors? The inverse. Give me some points on the inverse. 0, 0. Another. 0, negative 2. Instead of negative 2, 0, we'll have 0, negative 2. What about as x goes to infinity, y goes to infinity? The end behavior gets switched for the inverse, and so as x goes to infinity, y goes to? Still goes to infinity, yeah? But less steep. What about minimum? Probably a ballpark in the minimum. Instead of at x equal negative 1, it's probably at y equal negative 1. And instead of bouncing off x of negative 2, it's bouncing off y of negative 2. So like that, yeah? What kind of symmetry? About, not the origin, that's different. Y equals x. It's about y equals x. Why is that? Because besides obviously being visual, when we find an inverse, what do? Switch x and y. If I take this axis and put it up there, wouldn't it reflect right across the line straight through those two axes? Sweet. Yes, it would, Mr. Rickman, you bet. Okay. All right, now let's get into calculus of derivatives and inverses here. Say you have the old square root function, which is something like 1, 1, 4, 2, 9, 3. I don't know how many times I've graphed this in my life. Yeah. It looks like that. Wait. Precision is required. Would you please sketch in a tangent at x equal 9? Approximate the slope that looks like about. Actually, I don't need about. What's the slope? One-sixth, yeah? Derivative of root x at 9 is 1/6. Okay, would you now graph the inverse in a dotted line kind of fashion or some other color? Now, on my instructions, I said, would you sketch the tangent at the point corresponding to x equals 4? What point would correspond to x equals 4 on the original? Y equals 4. I'm looking for you to graph the tangent to the inverse at y equals 4. And like that. Now, the idea is to start to see, all right, when you take a derivative of an inverse, what happens? It surely has something to do with the original. What? Well, let's talk this slope. We said this slope is 1/6. What does this slope look like? Is it negative 6 over 1, which would make sense, perpendicular. No, it's not. What is it? It is 6. Now that, on one level, kind of makes sense. dy dx is 1/6, then when we do inverses, we are switching x and y, so dx dy would be 6/1, which is not what I meant to write, 6/1. So it's logical. Now, the only gotcha, though, is, yeah, so it's the reciprocal of the original derivative. Cool? But it's at a different point. I didn't find the derivative of the inverse at the normal point. I found the derivative of the inverse at the inverse. So then this is the idea. The derivative of the inverse is 1 over the normal derivative at the inverse point. Not the original x, not the same x. All right, now that's kind of wordy and not very mathy, so let's get mathy, shall we? That's my favorite. On the back side, let's prove or develop a more formal definition of the derivative for the inverse. Given that we just talked about if a function is truly an inverse, then when you put one into the other, they should undo each other and get x. This is the best place to start from for getting the derivative of the inverse. Use that to get a rule for the derivative of the inverse, please.
Why are you doing that? Yeah, no, me too. Do you like it? What? Just take what you're gonna do. What are you choosing? Did you visit all of them?
What? No. Wouldn't you agree that to get a derivative rule, I probably need to take that and take the derivative or differentiate. So if I take the derivative on the left side, that'll require chain rule. Derivative of the outside is with the inside the same times the derivative of the inside, which is f prime of the inverse. So the derivative of the inverse. On the right-hand side, the derivative of x is just 1. This is the goal. I want the derivative of the inverse. So isolate that. The derivative of the inverse is 1 over the normal derivative, the reciprocal of the normal derivative, but instead of at x, at the inverse point. And that's what we said on the previous side. It's the reciprocal of the normal derivative, but at an inverse point instead of a normal point. That is my intention in what goes here. The derivative of the inverse is this. The more you write it, the more you remember it. Okay. You with me? Now let's see how this works. Okay, so if I asked you to find the inverse derivative at 2, given the function, then this is the thought process I might go through. The derivative of the inverse. I don't actually need to find, ironically, you don't really need to find the inverse to do this. I can just say, I know that this is 1 over the normal derivative at the inverse at 2. Wait. Now, I guess you could go at this one of two ways. You could find the derivative, then find the inverse point, or find the inverse point. I typically work inside out. So let's pause here and say G inverse at 2. What is it? Now, you can look at this one of two ways. Isn't that, if I found the inverse, 2 would go in for x, right? Actually, maybe let's go here. Let's just do this. This might be a long way that we'll bypass in a second. But let's say I could find the inverse and say it is x equals G inverse cubed plus G inverse. Right? Are you with me? And that 2 is an x value. So I would say, all right, if I put in an x for 2, or 2x for x, then what would G inverse have to be? You'll see that this can usually be done by guessing check. And it would have to be 1, right? So G inverse at 2 would have to equal 1. Now, rather than do all that stuff, saying an x of 2 on the inverse, isn't an x of 2 on the inverse the same as y of 2 in the original? You with me? I mean, either way, I'm looking at saying, what happens what do I get when I cube plus itself equals 2? So I could just as easily say 2 equals x cubed plus x and solve that, and I still get, it's one of them. You with me? Questions? Okay, so going back to my derivative then, I need 1 over g prime at 1. Well, then you're home free. The derivative is 3x squared plus 2, plus 1, sorry. 3x squared plus 1, so your derivative, or your tangent slope to the inverse is 0.4. Now, all this is obviously notes purposes. You'll be able to find that inverse point a little quicker with a little bit of practice. So, towards that end, would you try that guy? Okay, so did you start with something like 1 over the normal derivative at the inverse? Basic idea, okay? At that point you need, what is the inverse at 2? That's like saying, instead of saying, what do you get when you have an x of 2 in the inverse, it's like saying, what's y of 2 in the original? So if I put a 2 into the original, what x would make that true?
0.
0, okay? So that is what is being put into the derivative in the denominator, is 0. At that point, you take the derivative, 1 over 2e to the 2 times 0, and therefore your answer is 1/2. We good? Okay. Slightly different variations, just mostly getting you to practice, and get it into your head. The more you write it, the more you remember. Try this one, please, which we actually have a different angle to check from.
Wait, Mr.
Yes, ma'am.
Would this work to do it? So I got that it was 0 and then So if I was reading here.
No. See, you never took, you left out this one. You never took the derivative of g.
Oh, I see. I
See what I'm saying?
Yeah.
That's not because that one gets, yeah.
Okay.
I'm usually a big notation fan, but I find the notation to this really clunky. It's too. It's not beautiful. Okay, now a good question in the last class was, well, how do you know that that's just the arcsine function-y kind of thing, pi over 3, and not lots of things, right? Are you with me? And I guess I didn't think of my notes to put this in, but if they're asking you, if they're using a notation for a function, then they usually are implying that the original function was 1-to-1, so that the inverse is a function. Do you need it? I should have put that in my pre-calc review too. Do you remember that stuff I'm talking about? Yes? 1-to-1 means for any one y, there is only one x. Now, in other words, the horizontal line test is passed. Now, that would make sense, because when you invert it, if the horizontal line test is passed, then the inverse will pass the vertical line test, and the inverse is a function. Okay, so I don't have to worry about getting lots of slopes here, because I'm not looking at an arcsine relation and saying, hey, look at all the places where root 3 over 2. Well, that, yeah, I guess that could be lots of different slopes. We're talking about the function form and 1. Okay? So, with that said, the answer to this, the inverse value is pi over 3, lava zone and all that stuff that Ms. Karen said. Yeah? Okay, so we have 1 over g prime at pi over 3, which is 1 over cosine of pi over 3, which is 1 over 1/2, which is 2. This is great, inverse the deal that we're dealing with. Could you have answered this question before today? This question, not those questions, this question. Yeah, what's the inverse? Arcsine. Okay, what is the derivative of arcsine? 1 over. And so what about g inverse prime at root 3 over 2? What is it? It's 2. So now that is obviously just arcsine. It doesn't necessarily play on those guys. Would you do that one more, and then we'll go on to a little different variety, and we'll be moving on. The goal is to get you to write this at least 5 times so it gets in your head. Ready? What was your inverse value? 0, true.
Oh.
So 1 over the derivative is 3 times 0 squared plus 1, so 1. Okay? Questions? All right, let's look at this from slightly different angles. Yes, sir.
There's a particular function that is like x cubed minus x, and two solutions. What would you like?
You would have to find them. So that's a good question. I am carefully choosing my functions so these are monotonic and they don't fail. But in that case, then it's time to solve a cubic and get every solution and find the slope at each stage. And I will maybe go there, but after practice. Okay? Let's try these graphical / numerical derivative cases, and then we will be done as dinner. Are you doing this analytically or graphically? Graphically,
I mean,
you
I
can
don't.
do it analytically. They both work. I think graphically is a lot less work. So if you do this graphically, you switch the x's and y's, get your new graph,
Oh,
and
I
find the
see.
slope at 2. So what do you say? Inverse derivative at 2 is 1 over 2. Okay? If you do this analytically, then you're saying something like g inverse's derivative at 2 is 1 over original derivative at g inverse at 2. You'd have to then say, all right, g inverse at 2 would be on the original graph when y is 2, what's x? And when y is 2, x is 1. And then you say, all right, what's the derivative on the original graph at 1, which is 2, and that in the denominator then is, yeah?
Wait, so how come you wouldn't find where y is 2 since it's the inverse? So it says x is 2 is where y
I actually did, when y is 2, and I found, and that's actually what I'm plugging in.
No, on like the graph. On like the graphically, if you did a graph.
The blue one?
Yeah.
That is the inverse, and so if I say what's g inverse at 2,
It's just where x
it is, yeah, it is when x is 2, what's y?
So it's when you do analytically.
I don't, crazily enough, I know what you mean. Try the last one, please, and then I think we'll have seen this from many possible angles and then solve it.
Okay.
What is g inverse at 2? Do I look at the edges of the table for 2 or the body of the table for 2? Do you have any idea what I'm just saying?
Body.
The body of the table for 2. Where's t on 2 on the g values? And that is at 1. And I put that into the derivative. G prime at 1 is sevens are x3. Is that going okay? Any questions? Okay, cool. Set. This is going to be so delightful. We are going to be caught up. Finally. I've dreamed about this day. 90. Questions on 90? 7. 7 is yes?
Yeah.
Okay, 7, 1. Okay.
I didn't get it. Oh.
10.
10.
10.
10. Oh, maybe 16 questions.
Okay, 16.
It's like a supplemental.
Oh, yeah, never mind. I was thinking of something. Okay,
15.
cool. 15?
15.
15?
15. 15.
Did I say it wrong? What are you talking about?
What's
Why do you keep saying 15 of me?
Oh my god, never mind. Yes. I thought you said 50.
Why would I say that?
I don't know. That's why I was confused.
Do I need to enunciate better?
Yes, Elizabeth.
Okay, sorry.
90 questions.
19?
I'm so confused.
18?
Whoa. I got
Maybe we won't, in fact, be. The other class had maybe 2 or 3 questions. Looking at these people that are back left corner, it should be. All right, here we go. 7 is. 7, no. Okay. The acceleration is 4 pi sine t. I didn't give you very much room in the box to work here. 4 pi sine t, velocity at time 0 is pi. Average velocity on the interval, v bar. Okay, how to get the average velocity, I either need position or velocity. Do you agree? Yeah, I can find average velocity by change of position over time or by average value of velocity. In terms of what's closest to what I have, I'm closest to velocity. I could get there quickest by acceleration. So velocity is the antiderivative of acceleration. And so with, did I copy that right? Or is it? Yeah, okay. Wouldn't you say that the antiderivative is 4 pi negative 4 pi cosine t plus c? Oui. And if v of 0 is pi, then pi equals negative 4 pi times cosine of 0 plus c. So c feels like negative 1/4, yes? If velocity then is negative 4 pi cosine t minus 1/4, now how do I find average velocity? The average value theorem. So the average velocity, which I'll call v bar, is 1 over pi minus 0 from 0 to pi of negative 4 pi cosine t minus 1/4 dt. Oui? Okay. So 1 over pi is fine. The antiderivative is negative 4 pi sine t minus 1/4 t from 0 to pi, and then evaluate correctly, and you're rolling. You good? I do apologize for not giving you more room. I imagine the sine expressions will drop out, and it'll just be about the t expression that's staying, yeah? Okay, moving on to 1. 1. How fast is the depth? Okay, the water's dripping out. If the water's dripping out, then that implies dVdt is negative 1 cubic centimeter per second. That's given. They want the height rate of change at the instant. The height is 2 centimeters. Wait.
Yeah.
Okay, so where did you get hung up here, people? Did you sub first? I hope you sub first instead of using 2 variables. And the relationship looks like the cone looks like this. So the diameter equals the height. So we could say the radius is half the height, yay?
Yeah.
If that goes in, then we get pi over 12 h cubed for our function.
Oh,
And that's cleaner. Yeah?
wait, h squared, right?
Cubed. R is squared and there's an h still there, so it should be
Oh, okay.
cubed. Yes.
So C equals pi. Because the first time is 0 is 1. And then, so 4 pi plus 5.
Ah, yes. Ah, you're right. So negative 4 plus 4 pi should be 5 pi divided by, so this is 5 fourths?
It's 5 pi.
What's the answer to
It's
that?
not pi by 4.
Oh, what am I, yes. I'm adding it over. Why am I dividing it over? 5 pi. Yes, what a dummy I am.
Here, I'll just.
So my key then probably is wrong, because that sounds like what I did on my
Oh,
key.
God.
Okay,
That's what it was.
so you are correct, I was incorrect. You're right, thank you, I rushed through it.
Wait,
Okay,
is that given?
okay, 10. Question on 10 on 90. Does anybody need 10 still? Okay,
No, I don't, okay,
yes, you do?
I don't get the K, how did you just come up with .1?
It's the percentage of straight.
Yeah, but how did you just come up with that? Because I solved it by doing my K equals natural log of 11
What did you get? K equals
natural log.
11 over 10.
Yeah, like how are you solving for K?
I am saying, so tell me this. Say you had $500 and the interest rate is 10%, then what is the next year's change? Or what's the amount next year is 550, yes?
Yeah.
Wouldn't you say the change then is 50? So you could say the rate of change is 10% of how much was there.
Isn't that overestimated?
No, it's true.
Then why would, like how can you?
So why doesn't your way work?
Yeah, because if you solve for it analytically,
So
slightly less than.
I disagree. So say you have this version, yeah?
Yeah, I guess.
Okay. So in what kind of case did you make up then? 10%? Did you do something like 1.1 is to 1?
No, it gives you like numbers.
They don't give you two cases, they just give you one, don't they? Oh, yeah, no, you're right. They give you no. Okay, my bad. Sorry, you're right. So they give you 1,100.
And 1,000.
Okay,
The case.
e to the k times 1. Yes. So 1.1 equals e to the kt. Natural log of 1.1 equals kt, k times 1 rather, sorry. So k is natural log of 1.1.
Yeah, but if you do that, it's less. It's like 0.9 C something or something like that. So how can both ways be true?
This feels like it's not right. Here's why.
Yeah. So what if this is? Oh wait, no, I see.
Let's see, what is this a log rule thing? So you put in log 1.1 and it is not 0.1.
But I just did 11, so maybe my math is wrong.
11 tenths is fine. A log of 11 minus log of 10.
Yeah, it's less than 0.1, so I don't understand how both can be correct. Yeah, but I get how you get 0.1, so then that's also correct. Which one is more?
Well, maybe I'm making a leap in.
Yes, and then in the high school, it's okay.
Okay.
judgment, but if I do any kind of amount work, isn't this always the interest rate? Right? So why isn't it e to the 0.1?
What is it always?
Oh yeah. So why isn't k coming out to be 0.1? Where's my error? I'll see. Okay, 10%. It's definitely growing by 10% in a year. Exponentiate, that's cool. Log. I'm not seeing why this is failed. I guess I'll have to come back to you. I don't see the issue right now. If I take 1,000 e to the 0.1, that's not 1,100, I assume. It's close, but not exactly.
It's 1,105.1709. It's too big, so it's zero. Well, I think the problem is that creating your payoff of just 2 instances, but if we have a third instance, it would probably show that it's not exactly 1.17261, but it just happened to be this.
No, it shouldn't.
Think about that. We're missing something, that's for sure.
Because it's just.
Let me think about it, I guess. For now, let's go with both, but I'll think about what's going on here.
Okay.
I have to come back to that. 16. 16 is 16 still a question? Okay, so you have this 1/2, and you're finding the volume 2 different ways. If it says using X,
Oh, I think I just need her B.
part B, the washers.
Yeah.
Okay. If you're using washers, then are you using X or Y slices?
Yeah, why?
Y slices, okay. So, if you use Y slices, are you getting one area or one integral setup or 2? Look at those slices. You have, in one case, you're from 2 to 1, 2 to 1, 2 to 1, but then you start handing off into a different situation, curve to 1.
So 2.
So you should have 2 integrals, both washers. So you should have integral pi r squared minus r squared plus another pi r squared minus r squared. With respect to y, what is the outer r and inner r in the lower section? Big R is 2 squared minus 1 squared. Okay, from 0 to this point, what is that point? Is that x equal 2? Or is that 2? It's an x of 2, but if x is 2 as in y equals 1 over x, then that is a y value of 1/2. And the next region is from 1/2 to, when x is 1, y is 1. Okay, what about the upper region? What is big R? It's from the axis to the curve, so it's varying x. In y terms, that would be 1 over y. And the inner R, always the same or varying? Always the same, that constant 1. Okay.
Okay.
How about 15? Is 15 still a question? 15? No? Don't?
Oh, I had a question about how to use the alternative term
You
to show.
do not have to show. If I ask you to prove, I'll say prove or show, but it's just find the x, find the y, or find the a, find the b. You don't have to prove. Okay? So you can just find derivatives at 1 and 7. Back to the change. Okay, 19, question on 19. Yes? Does anybody need 19?
Yes.
Okay. 19 is 3x e to the x squared. Is this integration by parts or u sub? U sub, yeah, let u equal x squared, and that should get you going. Might have been trying integration by parts. 18. 18 is x natural log of x. Now that is integration by parts, but let u equal natural log. dv equals x dx. That's Lipit kind of thing. Log is the best possible. All right. Well, I was so jazzed about getting caught up, but with your class, I'm not caught up. How come? I guess tomorrow, huh? Bless you.
I was a student.
All right. Yes.
So 25 on 7.
Yeah.
On the key.
Yeah.
You did that. You multiplied by 1 instead of negative. Why?
I divided by 1. Not negative 1?
I thought the parts only had to do.
No. You could divide by negative 2, and the goal would be to see is there a hole. But I kind of mentally just said 2's not happening, so I didn't ever do that. I didn't show it, because 2 didn't work. I could just look at it and see 2 didn't work. When I divided by 1, I was trying to see is 1 and x intersect. I'm trying to find zeros on the graph there, rather than trying to divide out the denominator. And so that's why I did that, so I could see that I have an x-intercept at 1. Also, so I could see if I had other x-intercepts. And because this quadratic had no real roots, there was only one x-intercept. For the asymptote, to get the actual asymptote, if they asked what is the equation of the parabolic asymptote, I would have had to have done this. But they didn't have it. They just said what's in behavior, and so I just said, it's going to be parabolic, kind of halfway there. Okay?
No, I'm okay.
Yes?
4, that's how it is. Except for this, I don't get that. I keep getting negative.
Yeah, you do go x over the x equal. Yeah.
Yeah, but that's just put a negative.
Or not the absolute value? No, that is what the absolute value. I mean, if I said, remember when we did piecewise, and if I said y equals the absolute value of sine, what is it piecewise? I would say it is the same as normal sine and then opposite sine. So I'm not fudging that. The absolute value is equivalent to the opposite where it is negative.
So I can't in this case just put a negative.
You can, but not the absolute value step. You were saying put it here.
Go put it here.
Yeah, when you go from that value to function, then it's there wasn't any back then. Did you say yes, Rosie? Yeah. Oh, print it out.
You didn't do it. I could tell.
I think she was absent yesterday, wasn't she? Okay, so yesterday was 91. So I need to print that. I lost, but I don't have enough of those. So I'll print you one of those. And did I not stop this?
2 hours.